Hi, everyone. Welcome. I think we'll get started. Thanks to everyone for coming. Today, I'm going to be talking about how Lyft has rebuilt our streaming platform using Flink on top of Kubernetes. And my name is Micah Wylde, and I'm from the streaming platform at Lyft. So just to give you a brief overview of what we're going to be talking about today, I'm going to start by talking a little bit about how we use Flink at Lyft, why Flink is really important to us. Talk about why we decided Kubernetes was the right option for migrating all of our Flink workloads to. Give a brief overview of Kubernetes for those of you who haven't worked with it before. And then I'll wrap up by talking about the Flink Kubernetes operator that we've built in order to run all of our Flink workloads. So to kick things off, why do we use Flink at Lyft? Why is Flink so important to us? So for those of you who don't know, Lyft is a ride-sharing platform. We're the second largest ride-sharing platform in North America after Uber. And as a ride-sharing platform, real-time data is really, really crucial to our product. When someone is sitting there with their phone and they want a ride from the bar, they want the ride immediately. They don't want us to sit there, wait a day to churn through our data. They need it right then. And that means that a lot of our systems also have to be real time. Just some examples of where this kind of comes up in our product. Places like our dynamic pricing algorithms, which balance supply and demand in the marketplace and make sure that there's always enough drivers for the riders who want to take a ride. For calculating dynamic ETA. So we know if there's a traffic accident, we need to be able to incorporate that into our ETA predictions as quickly as possible so that we're able to give accurate estimates and accurately priced rides. For fraud, people are constantly trying to take advantage of us and steal money from us. We have to be able to detect that in real time. And then for various kind of other product enhancements, like our top destinations feature, which kind of predicts where we think you might want to go, or for other kind of user delight, giving people coupons, detecting that you've kind of met some promotional criteria. And then on the driver side, this powers really crucial features like we have something called ride streaks, which basically give drivers benefits for driving a lot in a row, or things like our marketplace controls that help balance supply and demand. Then kind of internally, this also powers our real-time ETL system, which if you came to the talk yesterday, you would have heard more about. This has really transformed how we consume data for analytical use cases at Lyft, where thanks to Flink, we can now query all of our data within 5 minutes of it landing, which is really crucial for running a dynamic marketplace and being able to respond quickly to new market conditions. So in total, we have more than 80 Flink jobs running in production. We have over 50 engineers who are developing Flink-based streaming applications. And across all of our jobs, we're processing tens or even hundreds of millions of events per second. So really, really high scale and really crucial to the success of Lyft. We've developed kind of 3 different models for running Flink and streaming applications at Lyft. The first is kind of people are probably most familiar with what we call Flink as a framework. In this model, we provide kind of the basic infrastructure for people to run Flink. Developers write normal Flink Java applications. You have the full power of all the different Flink APIs available, and teams are responsible for kind of owning and operating their own applications. However, Lyft is primarily a Python shop, so Java is not like the most useful API for a lot of our engineers. So over the past year or two, we've been rolling out Beam Python as another option for running Flink applications. So now You can write applications in Python. You have a wonderful API that Beam provides for you that exposes a lot of the power of Flink. And we can run it on top of all of our existing Flink infrastructure using Beam portability. And then the third model is what we call Dryft. This is our in-house streaming SQL platform. So for people who are not engineers, who are maybe data scientists or analysts who don't want to write Python or Java, we provide a really simple SQL interface where you can still take advantage of all of this streaming data technology. So why did we decide to migrate all this stuff to Kubernetes? So for those of you who run Kubernetes, who've run Flink, this diagram may look familiar. This is just kind of the rough topology of a Flink cluster. So we have two different types of nodes. We have a job manager that's kind of responsible for kind of managing execution, for keeping track of all the workers. And then we have the actual worker nodes, the task managers, that actually run the user code. So in our kind of legacy deployment, pre-Kubernetes, we deployed all of these things onto raw EC2 nodes. We'd have an elastic load balancer in front of a job manager, and then a handful of task managers. The deployment process on top of this infrastructure was pretty finicky. We had a bunch of different steps. Started with a Jenkins deploy, which would kind of deploy the actual Flink application jar to S3. Then we'd have salt code on the job manager that would kind of be pulling this from this like new file from S3 periodically, and would eventually update the jar on all of our instances. And then the user would have to like run a series of bash commands to actually like do the update, to cancel the existing job, restart the cluster, and then submit the new job with their new code. This has a lot of downsides. It's kind of a convoluted process for users with a bunch of different steps. It's also kind of error prone. Lots of things can go wrong, and there isn't much support for users to kind of be able to deal with those things going wrong. It also, because of our, we're waiting for EC2 instances to come up, and we have a long, complicated provisioning process for nodes. It would take about 20 minutes to replace nodes. So if a node died, there's potentially a long wait, potentially with the job down, before we could get those nodes back up. And it just required a lot of infrastructure for kind of every single job. We have ASGs, we have ELBs, we have DNS, and it made it very hard to kind of be more dynamic with our infrastructure. It's very static. We also had kind of this Lyft specific notion of like a service, which was like very statically tied into like a single Git repo would be a single service, which would end up being a single Flink cluster, which meant that like if you wanted to like run an experimental job, or you wanted to do a backfill or something, it was really hard to kind of set all of that infrastructure up. It required a lot of code, it required a lot of time. On Dryft, which is our managed SQL platform, we had to run a single cluster for all of the different jobs because it wasn't practical to kind of build up all this infrastructure on a per job basis. That meant we were running 60 plus jobs on a single cluster. And Flink is technically a multi-tenant system, but if you've ever tried to do this, you know that it's fire. Everything was blowing up all the time. Really hard to make this stable. So on Kubernetes, by contrast, we have a single configuration in one place that can create all of the cluster resources and manage the job, everything in a single place. We have a more flexible deployment model. We can support things like managed services like Dryft, support ad hoc applications, experiments, backfills. We can create new clusters very quickly, under 2 minutes, and we can automate this whole complicated update process. So that's why we're excited about Kubernetes. What is Kubernetes? Probably heard a lot about it. I think it's been inescapable in the industry. What actually is it? So I took this quote from the Kubernetes website. Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. What does that mean to us? So just kind of like sketch the history of these systems. Back in the day, 15 years ago, if you wanted to run some kind of web service, you would go call up a company that made servers, Dell or Supermicro, whoever, and you'd go call up a colocation facility and you'd go rack up your servers. And then maybe 3 months later, after you decided you wanted these servers, you'd actually have them and you'd be able to do something with them. And because those servers were really, really hard to like scale or change, they tend to be really statically allocated to a particular service. If a server hosted your MySQL, it was your MySQL server forever until you decommissioned the hardware. In the mid-2000s, we started shifting a lot of workloads to cloud VMs. These were really exciting because you had an API where you could just immediately get resources. You didn't have to like negotiate with your company's CapEx department or whatever. Just immediately hit an API, you have servers. And because of this, we tend to be much more flexible. You could rescale stuff, you could migrate use cases around. And so these VMs tended not to live as long as our old servers. Kubernetes is kind of an extension of all of these trends. Now you can provision resources in seconds instead of in minutes. And the resources tend to be statically and immutably assigned to a particular use case, typically a particular version of your application. So every deploy, you get completely new resources and they're completely immutable. So what is Kubernetes? It's basically a combination of two things. It's a configuration store and a set of controllers. The configuration store in Kubernetes is etcd, which is a consistent database with a REST API in front of it. And then these controllers are pieces of software that basically execute this basic control loop, where on each iteration of this, you first observe the environment, observe your configuration, and then act to bring the environment in concordance with your configuration. So if I want a new cluster resource, I'll create a new configuration for that cluster resource. And in the background, a controller will notice that that resource was created and will go and actually affect the environment, actually go provision the actual resources on the cluster in order to bring the cluster in concordance with that configuration. This is actually a really powerful way to kind of think about managing resources, very, very general across all the different kinds of things we deploy. So just as an example of what this looks like, in EC2, if we want to get a new instance, we'll call an API, the run instances API. It'll sit there for a while, and a few minutes later, it'll come back saying that it's like booting up the instance, give us some ID, we can go check on it. Kubernetes, this looks pretty different. Instead of actually talking to an API and saying what we want, all we do is we create this configuration and we push it to the API server. When this returns, all that we get back is a success saying that we successfully pushed this configuration, but nothing's actually happened yet. All that's happened is we've updated our database. And then in the background, the pod controller, pods are the Kubernetes equivalent of EC2 instances. The pod controller notices that there's a new pod configuration, and it goes and creates a node, schedules it, does whatever it needs to bring the cluster up to date with the configuration we've created. So Kubernetes operates off of a notion of resources. There's a handful of kind of standard resources that everyone will use. The simplest of those is a pod. Pod, I mentioned, is roughly equivalent to an instance in kind of EC2 or cloud terminology. Represents a group of one or more containers scheduled onto a single node, the single unique IP. One thing that's different between pods and maybe how you think about EC2 instances is that pods are mortal. They're expected to die, they're not resurrected, and your system has to be able to handle that. So in order to kind of build reliable systems on top of these ephemeral pods, Kubernetes provides something called a replica set. This is very similar to an autoscaling group, if you know of EC2. It basically is a pod definition along with a number, which is the number of those pods that you would like. And the replica set controller, when it sees you want 4 of these pods and there's actually 0 of them, it'll go and create the pods so that the configuration matches the environment. Because these pods are constantly coming and going, you need a kind of consistent way to refer to those pods. That's a service. It's just a logical grouping of pods with a name. It frees kind of callers of services from having to think about the kind of individual pods. You just say, I want MySQL, and the service kind of is responsible for getting your requests to the actual pods that host that service. So takeaway, Kubernetes is a consistent API to all of your cluster infrastructure. Whatever kind of infrastructure you have, whether it's a instance, it's a database, it's a Flink application, Kubernetes provides a consistent way to create and manage all that infrastructure. The other thing that is really surprising about Kubernetes is that all of these operations happen asynchronously by these controllers that are driving to the cluster to a desired state from your configuration. So how does this work for Kubernetes? There we go. Okay. So to understand kind of what we've done to run Kubernetes on top of, or excuse me, to run Flink on top of Kubernetes, I have to talk about one more type of resource. This is the custom resource definition. It's an extension mechanism that Kubernetes provides that allow users to create kind of their own resource types on top of Kubernetes. So Kubernetes doesn't know about Flink applications, of course. It basically, out of the box, just knows how to deploy stateless microservices. So using custom resource definitions, we're able to kind of teach Kubernetes about these other more complex applications that we'd like to run. And then the community has kind of taken this notion of custom resource definitions and custom controllers and found that when you bundle those things together, you get a really powerful pattern, which is called the operator pattern. So why did we decide to build an operator for Flink? There's a few different ways you might run Flink on Kubernetes that people were doing. If you look at the official Flink documentation, they suggest this kind of Helm approach. Helm is kind of a Kubernetes package manager. It gives you kind of one command to run complex things on Kubernetes. And you can use that to kind of create a Flink cluster, and then you can deploy your applications to that. We decided not to go with that approach because it doesn't really answer kind of the hard questions about how do you run an application over kind of the long term as it is updated, as it's scaled up, scaled down. How do you make all that stuff work really well? Helm kind of just answers the question of how do you get the cluster in the first place. Flink now also, as of the 1.10 release, has experimental native support for using Kubernetes as a resource manager. This didn't exist when we started this project. I think it's really exciting. But at the same time, I think there still are some significant advantages that an operator gives you. So the key thing that an operator provides is it basically is a way to automatically encode the operational knowledge that your team has. So my team at Lyft has a lot of experience running Flink applications reliably, which our users typically don't have. So by building an operator, we're able to basically automate to writing code all of that experience and provide really reliable Flink infrastructure to our customers. This This may be something slightly different about how Lyft uses Flink than some other users. But for us, uptime and reliability are absolutely paramount. If Flink applications are down at Lyft, there are major consequences for our engineers and for our platform and for our users. So we've put a lot of energy into making sure that we are able to run these applications over the long term as reliably as possible. A big part of that is making updates reliable. Lyft engineers are used to updating applications on a daily or weekly basis, and that's usually when something will go wrong. So in order to make that experience as good as possible, we developed this Flink application custom resource. You can go check it out at that link. It contains all the configuration you need to create a Flink cluster, launch a job, and manage its lifecycle. Minimum, this is pretty simple. You just need an image, a jar name, and an entry class. But we support kind of the full spectrum of Flink configuration as well. So it looks like this in the very simple case. You have a straightforward word count application. Every Kubernetes resource has a handful of common fields. You have a kind, which in this case is Flink application. You have some metadata like the name of the application. And then you have the spec field, which contains all the information that your controller needs to set up your infrastructure. So in this case, it's stuff like the image that you're going to use, the jar name that you'd like to submit to the cluster, parallelism, which determines how large the cluster is, and so on. So the Flink application custom resource defines the kind of desired state of the deployment. Well, the operator is responsible for evolving the environment to that state. So some examples of what that looks like, because as I mentioned earlier, every operation in Kubernetes must be triggered by a modification to a resource. So this means that operations work kind of differently than you might be used to using like the Flink command line tooling. So for example, to run a new job using the command line tools, you'll call this Flink Run command with a jar. It'll submit it to a job manager, which will go fan out the work to all of your task managers. In Kubernetes, you define your configuration, you put it to the cluster, and then in the background, the operator sees that there's a new configuration, it goes and creates the cluster, submits the job. In the update case, I mentioned earlier, we have like in our legacy platform, we had these like bash jobs that tried to automate this process. It's fairly complicated. You have to update the jar, you have to cancel the job with a save point, restart the cluster, and then submit the job with the new code and the save point. So now we replaced that with a really simple, you just update the part of the config with whatever changes you'd like. And the typical case is just with a new image. Or it can be as complicated as updating Flink configurations or updating resources or updating parallelism. And in the background, the operator is going to kind of go through a state machine to kind of get the new job running with the new code. As part of this, we always start with bringing up all the resources for a new cluster. So we don't reuse our cluster. Kubernetes lets us treat infrastructure as ephemeral. So we're able to basically always have new, clean infrastructure whenever we do a deploy. We bring that up first so that we know that the resources are there when we'll need them. We don't have to wait for that. Then we save point and cancel the existing job, then submit the new job to the new cluster, and then hopefully everything went great and we're in the running phase now where kind of it's just steady state going on. Of course, in practice, there's a lot of stuff that can go wrong here. When we try to create the cluster, maybe we can't get resources and the cluster doesn't come up successfully. We might fail to save point the job because there's back pressure or whatever. We might fail when we submit the job because it's not state compatible with the old version, or there might be an exception thrown in the main method or whatever. And if any of these things happen, the operator knows how to roll back so that we are able to get back to a good place. So the goal of all of this is that whatever the user does, no matter how badly they've screwed up, or whatever the state of our environment is, if once you do an update, once this completes, we should always be back in some kind of good state. Hopefully that means that your new code is running, but if for some reason that's not possible, we'll make sure that the old code is running and that the job is still up and processing data. So a kind of key part of making users successful with all of this, as I mentioned earlier, all of these operations happen asynchronously, which means that the user doesn't get kind of immediate feedback that like something has happened. Kubernetes provides a few different mechanisms to give users that feedback. One of those is the status field in the custom resource. Most Kubernetes objects have a status field that is both a way to communicate with users about kind of the state of their resource, as well as actually the internal state of your operator. So this status field has all the information the operator needs to know about this Flink application in order to know kind of what to do in every situation. So one thing to one of the most important things here is this last line, the phase, which tells the operator where in that state machine this application is, what it needs to do next. The other feedback mechanism Kubernetes provides out of the box is events. So events are kind of special objects that can be tied to another Kubernetes object and basically just provide a way to tell the user what's going on in the system. So the operator will create an event when it does anything with an application, and we can show those to the user, let them see what's happening as we're kind of going through all these phases of an update. But so Kubernetes provides kind of out-of-the-box tools to deal with things like updating resources, getting resources, deleting resources. But those tools tend to be pretty low level. And we found that it was really hard to train users to be successful with those like out-of-the-box generic tools. The other thing is that your Kubernetes configurations can get very complicated, very big. Kubernetes only provides YAML as a configuration language. So there's no ability to really like abstract out common configuration, support things like different environments. As a platform team, we don't really have the ability out of the box to kind of provide a common configuration to our users that they can build on top of. If you see here, this is what kind of the raw configuration for one of our applications looks like. It's a lot for a user to kind of manage and understand. So we've adopted a programming language called JSONet in order to generate these configurations based on platform level configurations, and then application and environmental configurations. It looks like this. So instead of having to define that whole hundreds of lines of YAML, you kind of just define the stuff that is relevant to you and your job. And you can kind of build that on top of the common platform configuration. Then in concert with that, we provide a command line tool that basically simplifies a lot of these operational tasks, kind of interacting with Kubernetes, while also providing better feedback so users can understand what's happening. So it provides all these different commands for interacting with your cluster. Example of what this would look like doing an update. I mentioned earlier the kind of built-in Kubernetes tooling. When you, for example, create an application, it would just tell you that it successfully created the configuration. but it doesn't tell you anything that's actually happened. Like maybe there's a problem, but you wouldn't know unless you actually like went and dug in to all of the cluster resources. So we found it was really important to like be upfront with our users about what's actually happening. So when you do an update using our tooling, we'll actually go and like watch the deploy. We'll see every step that happens. We'll stream back those events to the user. And when something goes wrong, we'll tell them whether the deploy was successful or not. It's also really important for hooking into our CI system so that users know that the deploy was successful. So in a failed case, this also allows us to kind of stream back errors and tell them exactly what went wrong. So in this case, the user tried to do a deploy, but it turned out it wasn't state compatible with their existing application. So we roll back the job to the old code so that it's still running. And we tell the user what went wrong so that hopefully they can fix it. So the operator is open source. It's on GitHub. We've had a lot of contributions from a bunch of different companies, and we're always looking for more use cases, more deployment environments. Please come and check it out. So we've been successful in rolling this out at Lyft. Today, the vast majority of Flink applications run on this new Kubernetes-based deployment model. Doing so, we found definitely had some challenges. I'd say like the biggest challenge is just that Kubernetes is really, really big, really complicated. For end users, it's a lot to learn. We found it's really crucial to simplify as much as possible and not expose more of Kubernetes to your users than they absolutely need to know. There's also ways in which Kubernetes is not really well optimized for kind of this use case. It was kind of designed for running stateless microservices. When you're doing things that are sort of stateful, like Flink applications, this can run into problems. Like Kubernetes expects to be able to kind of kill pods at any time, which for Flink applications causes restarts. This happens too often, you might never really make progress in your job. There's also some challenges running JVM and containers. It's getting a little bit easier, but it's not the environment that the JVM was kind of designed for. So there's some problems with like memory configurations you need to keep on top of. And then it's kind of challenges around immutability in general. It makes things like development and debugging a lot harder. We're used to being able to, copy some code to a server and restart stuff and hook up a debugger and all that in order to debug issues. That's gone a lot harder now in Kubernetes. Some of it is still possible, but it's not going to be as straightforward as when you had kind of static servers. And so as far as our next steps, this platform has given us the ability to do a lot of really powerful kind of automated operations. One thing we're really excited about is building auto-scaling into this, having kind of better support for like ad hoc, backfill, experimental jobs, support for Flink batch jobs, something we've never tried at Lyft, but we're really excited about the potential there. And then to kind of get the next level of reliability in our system, doing things like automated disaster recovery. If we like lose a Kubernetes cluster, if we lose an availability zone or even an entire region, we know to automatically and quickly recover from those situations. So that's all my slides. Thanks everyone for coming.